ever take apart a smartphone. I mean, just imagine all those tiny components, like perfectly placed. They have to be so precisely calibrated.
Yeah, definitely.
It's incredible. You tweak one tiny resistor and the whole thing, poof, it won't even turn on.
Right. The tiniest things can mess everything up.
And that kind of sensitivity where the whole system, it just hinges on these exact values of so many different parameters.
Mm. Well, that's kind of the idea behind what we call fine-tuning.
It is. And
Yeah.
it gets really interesting philosophically. I mean, when you take that idea and apply it to the entire universe, the whole cosmos.
Oh, absolutely. We're not talking about circuits and chips anymore, but like the fundamental fabric of reality, the laws that govern everything.
Exactly. The constants that shape those laws. Even the initial conditions way back at the Big Bang. It's like the universe's starting point was also fine-tuned.
And get this, the universe's ability to actually host life, any kind of life, not just us humans, seem to depend on a crazy, delicate balance of all these fundamental features. It really does. Physicists have found some wild examples where even the slightest change, a tiny tweak, would make the universe completely sterile. No life at all.
It's mind-blowing, isn't it? And that's why this topic is just a goldmine for philosophical debate.
For sure. So, is our life-filled universe just a massive fluke, a one in a gazillion cosmic lottery win?
Or could there be something deeper going on, some level of physics we haven't discovered yet, that actually dictates these very specific values?
Maybe. Or perhaps, and this is a big one, maybe it hints at something more purposeful, a deliberate design even.
Right, like a cosmic architect. And there's the idea of a whole bunch of universes, a multiverse, where most of them just didn't get the life-supporting settings right.
A cosmic landscape of possibilities.
And for you, our listeners, with your philosophical minds, this isn't just about accepting what science tells us. It's about really digging into the logic.
Absolutely. Questioning the assumptions, exploring all the different philosophical interpretations we can bring to these incredible scientific discoveries.
That's what we're here for. So in this deep dive, we're going to unpack the concept of fine-tuning, how it applies to life in the universe.
We'll show you the evidence that physicists have gathered,
Okay.
and then, keeping in mind your philosophical toolbox, we'll jump into the major philosophical responses to this fine-tuning.
Exactly. We'll explore the strengths, the weaknesses, the arguments, the counter-arguments. It's going to be a wild ride.
Let's do it.
All right, let's start with the evidence for this fine-tuning for life. The main argument, as we've said, is that life, anything we could recognize as life, just couldn't exist if the universe's fundamental properties were even a little bit different.
Yeah, that's the core of it. And what's really fascinating from a philosophical standpoint is that these arguments try to demonstrate that the vast majority of universes, like if you imagine universes with different laws or constants, most of them would be completely barren.
Totally empty.
No life at all. They wouldn't even have the basic ingredients for life, like stars, galaxies, even stable atoms. It's pretty profound.
Okay, so let's talk about gravity. It's the force that holds the entire universe together. And its strength, compared to another force, electromagnetism, seems to be absolutely vital.
It really is. It's all about the balance between the two. If gravity was way weaker, matter wouldn't have clumped together to form galaxies and stars.
Yeah.
And without stars, you have no energy source and no supernovae.
No supernovae, so what?
Supernovae are crucial. They're like giant cosmic factories. They create heavier elements, the kind we need for life, carbon, oxygen, all that. And then they spread those elements throughout the universe.
Wow, I never thought of them like that.
Yeah, they're essential. And it's not just that gravity exists, but that its strength is so incredibly fine-tuned.
So walk me through this fine-tuning. What if gravity was a bit weaker? Not a lot, just a bit.
Okay, so imagine gravity a little weaker. Stars, even stars like our sun, they might burn much cooler and never go supernova. That means those heavier elements they make wouldn't get scattered around, and there wouldn't be enough for planets to form, let alone life.
Okay, so no planets, no life. What about if gravity was stronger?
Well then, stars would form from much smaller clouds of gas, so you'd end up with tiny stars that don't last very long. And life, as we understand it at least, needs billions of years to evolve. So, a universe with short-lived stars, not good for life.
So gravity has to be just right, and it's not just gravity, right? This fine-tuning thing applies to other forces, like the strong nuclear force.
The strong force, yep, that's the one that holds the nucleus of an atom together. And its strength, compared to electromagnetism again. It's really critical. Let me explain. Electromagnetism at very short distances wants to push those positively charged protons in the nucleus apart.
Right, like charges repel.
Exactly.
Right.
So the strong force has to be strong enough to overcome that repulsion and keep the nucleus stable. Now, imagine if the strong force was, let's say, 50% stronger than it is.
50%, that's a big jump.
It is. And in the early universe, almost all the hydrogen would have fused into helium right away.
Okay, so lots of helium, so what?
Well, it would leave almost no hydrogen left over. And we need hydrogen for those long-lived stars like our sun. They use hydrogen as fuel, slowly converting it to helium over billions of years. Without enough hydrogen, you don't get those stable, long-lasting stars.
So too much helium means not enough fuel for the good kind of stars. What if the strong force was a bit weaker?
Even a little weaker. And the fusion process in stars, how they create heavier elements, would become extremely inefficient.
So we'd have a universe with mostly hydrogen and not much else.
Basically. And we need those heavier elements for complex chemistry and ultimately life. It's incredible. Even tiny changes to the strong force could make the formation of things like carbon and oxygen inside stars impossible.
And those are pretty important for life as we know it. It really does seem like the universe is set up just right.
It does. It's like a delicate recipe, and the ingredients have to be perfectly measured. And this fine-tuning, it goes beyond the forces to the masses of the fundamental particles too, things like quarks.
Quarks, right, the tiny particles that make up protons and neutrons.
Yeah, and the difference in mass between the up and down quarks, it seems tiny, but it has a huge impact. It affects the stability of those protons and neutrons, especially when you consider the weak force.
So if you messed with that mass difference,
you might end up with protons decaying into neutrons, or the other way around, and that would lead to a completely different kind of universe, maybe one with much simpler atoms, or maybe no stable atoms at all. And without stable atoms, you can forget about life.
So no protons, no atoms, no life. Got it. What about the electron? Its mass also matters.
Oh, absolutely. The electron's mass is much smaller than that mass difference between the quarks, but still really important. If the electron was a bit heavier relative to the quarks, it could also mess up the stability of atoms. It's amazing how these tiny mass differences have such big consequences.
It's like a giant domino effect. Okay, so we've talked about gravity, the strong force, quarks, even the electron. What about the weak force?
The weak force, that's an interesting one. It's not as obvious in our everyday lives, but it's still vital for life. It's involved in the process of radioactive decay and plays a key role in how stars fuse hydrogen into helium.
Okay, but how does its strength affect the possibility of life?
Well, if the weak force was much weaker, let's say 10 times weaker, the early universe would have ended up with way more neutrons than protons.
Interesting. What would that do?
It would lead to the quick formation of heavier hydrogen isotopes like deuterium and tritium, and eventually you'd get a universe mostly filled with helium.
Okay, so back to the helium problem again.
Kind of. See, long-lived stars like our sun need that slow, steady process of converting hydrogen to helium. It's like a slow burn that keeps them going for billions of years. The weak force controls that process. If it's too weak, you don't get those stable, long-lasting stars.
So the weak force has to be just right, too, to keep the stellar engines running.
It does. It's another example of how these seemingly unrelated parameters are all interconnected. And then, of course, there's the cosmological constant, which is a whole other level of mystery.
The cosmological constant, that's the energy density of empty space itself, right?
Yeah, it's this weird energy that's everywhere, even in a perfect vacuum. And it's been one of the biggest puzzles in physics. Our best theories, based on quantum field theory, predict a cosmological constant that's vastly larger than what we actually observe, like ridiculously larger.
So how much larger are we talking?
Depending on the specific theoretical framework, we're talking about factors of 10 or even, it's almost impossible to grasp how huge that discrepancy is.
That's massive. So why is the observed value so much smaller? And how does that tie into the fine-tuning argument?
Well, if the cosmological constant were even slightly bigger than it is, like a few orders of magnitude, the expansion of the universe would have been so fast that gravity couldn't have pulled matter together to form galaxies.
We just have a big, empty, rapidly expanding universe.
Exactly. No galaxies, no stars, no planets, and no life. Some researchers have explored whether this constraint might be relaxed under certain very specific conditions in the early universe, but the basic point is that the cosmological constant, as we observe it, is unbelievably tiny compared to what our theories predict, and it just happens to fall within this very narrow range that allows for the formation of structure in the universe.
Wow, it's like we dodged a cosmic bullet.
It does seem that way. And beyond the fundamental forces and constants, even the initial conditions of the universe, right after the Big Bang, had to be very specific.
So it's not just about the laws themselves, but how the universe started out.
Exactly. Consider the overall density of energy in the early universe. It had to be incredibly close to the critical density, which is the perfect balance point between the universe that expands forever and one that collapses back on itself.
So it's like a cosmic tightrope walk. What if the density was off, even a little?
If it was just a tiny bit higher than the critical density, the universe would have been pulled back together by its own gravity, collapsing long before stars and galaxies could form.
A cosmic crunch.
Yeah. And if it was a fraction lower, the universe would have expanded way too fast. Matter would have spread out so thin that galaxies and stars wouldn't have been able to condense.
So it had to be just right, this Goldilocks density. What about those tiny fluctuations in the early universe, the things that eventually grew into galaxies and clusters?
Yes, those are really important. They're quantified by a number called Q, which is roughly 2 times 10^5. It basically measures how lumpy the early universe was. These tiny lumps, they acted as seeds for all the large-scale structure we see today.
So if Q was smaller, no lumps, no structure.
Pretty much. Gravity wouldn't have been able to pull things together fast enough. We'd have a very smooth, boring universe.
And if Q was bigger, more lumps.
Then gravity would have taken over too quickly. Those lumps would have collapsed into giant black holes before they could form stars and galaxies.
So Q had to be just right, too, to get the right balance of structure. It's amazing how all these things are interconnected, and we haven't even talked about entropy yet.
Entropy, yeah, that's a big one. It's basically a measure of disorder or randomness. And the early universe had to have incredibly low entropy, meaning it was highly ordered.
Why is that important for life?
Well, a high entropy universe would have been chaotic and unpredictable. Not the kind of place where complex structures like stars and galaxies could form.
Yeah.
Roger Penrose, he's a famous physicist, he calculated that the specific state of our early universe was incredibly improbable, like 1 in 10.
That's a ridiculously small number.
It is. It suggests that the early universe was in a very special, very ordered state, which was necessary for the emergence of complexity and ultimately life.
Okay, so we've looked at the fine-tuning of specific numerical values, the forces, the constants, the initial conditions. But what about the form of the laws themselves? Are those also fine-tuned for life?
That's a great question. Some philosophers and scientists argue that the very structure of our laws, the fact that we have gravity, the strong force, electromagnetism, and the weak force, with their specific properties, is itself a prerequisite for life. It's hard to imagine a universe where you just remove one of these fundamental forces and still get anything remotely like life.
But what about the weak force? We said it was important for stars, but is it really essential for the very possibility of life?
That's a good point. The weak force seems to be the least obvious in terms of its necessity for life. Some theoretical work suggests that you might be able to create a universe without the weak force, but with the other parameters adjusted, and still get a habitable universe. But it's still pretty wild that its strength, as we observed it, is so finely tuned for the type of stars we need for life.
So maybe not strictly necessary, but still fine-tuned. And there are other principles, like quantization and the Pauli exclusion principle, that seem pretty fundamental to life, right?
Absolutely. Quantization, the idea that energy comes in discrete packets, is essential for the stability of atoms. And the Pauli exclusion principle, which prevents certain types of particles from occupying the same state, is crucial for the structure of atoms and the behavior of matter. Without these principles, the universe would be a very different and likely much less hospitable place.
Okay, so we've seen a lot of evidence for fine-tuning, but a big question that keeps coming up is, are these conditions truly fine-tuned for life? Maybe they're just necessary for any kind of complexity or structure, and life is just one possible outcome.
That's a really important point, and one that sparks a lot of debate. The examples we've talked about, they generally point to conditions needed for life in a very broad sense, not just human life. The idea is that universes with very different parameters wouldn't have any kind of life, no matter how alien or different from us it might be.
But how can we be sure? We only know of one example of life. Us. Maybe we're underestimating how adaptable life could be. Maybe there are weird, unimaginable life forms that could thrive in completely different conditions.
It's a fair challenge. But the counter-argument is that universes with vastly different parameters probably wouldn't have the basic building blocks for any kind of complexity. Think about it. No stars for energy, No galaxies for stable environments, no stable atoms to form molecules. That sounds pretty hostile to life, no matter how you define it.
Okay, so the lack of basic ingredients would be a major problem. Now, some critics, like Victor Stenger, have raised concerns about the fine-tuning argument. What are some of their main points?
Stenger argues that the laws of nature might be more constrained than we think, maybe by some fundamental principle that forces them to be the way they are. He suggests this idea of point of view invariance, which means the laws shouldn't depend on the observer. He thinks the laws we see might be the only logically consistent laws possible.
So maybe there's less freedom for variation than we think.
That's Stenger's argument. But Luke Barnes, another physicist, he pushes back on that. He says that Stenger's confusing general principles with specific properties of our universe. He thinks there could be other consistent laws of physics. They just wouldn't lead to a universe like ours.
So the debate is about how much freedom there really is in the laws of nature.
Right. And Stenger also criticizes the way we usually test fine-tuning. We tend to change one parameter at a time and see what happens.
One at a time, why is that a problem?
He argues that maybe the life-permitting region is actually much larger if you change multiple parameters at once. Maybe there are combinations of values that work even if the individual values seem fine-tuned.
Okay, so maybe we're missing some hidden flexibility.
Maybe. But Barnes points out that there have been studies where they vary multiple parameters together, and the life-permitting region still seems surprisingly small. So it's an ongoing debate.
It's fascinating how even the methods we use to study fine-tuning are up for debate. And then you have someone like Fred Adams who offers a more nuanced view.
Adams, he's interesting. He warns against going too far with the fine-tuning claims. He thinks the range of parameters that could allow for life might be bigger than we think. He even suggests that our universe might not be the most life-friendly one possible. Maybe some tweaks would make it even better for life.
So we're just kind of average on the life-friendly scale.
Maybe. He calls our universe garden variety habitable. Not perfectly fine-tuned, but good enough for life to emerge.
Okay, so lots of back and forth on how finely tuned the universe actually is. But even if we grant that it's pretty finely tuned, does that automatically mean we need a special explanation for it? Could it just be a coincidence?
That's the core philosophical question, isn't it? Is this apparent improbability just a brute fact? Or does it demand an explanation beyond mere chance? Like, do we need a designer, a multiverse, or something else entirely?
It's like flipping a coin and getting heads 100 times in a row. It's improbable, but it could happen.
Exactly. Any specific sequence of coin flips is improbable before you flip them. But once it's happened, we don't usually search for some hidden cause. Stephen Jay Gould argued that maybe the universe is similar. Maybe it's just a rare, lucky outcome, but nothing more.
But some philosophers, like John Leslie, they say that just because something's improbable doesn't mean we should ignore it, especially when we have possible explanations available.
Right. Leslie's point is that if we have plausible explanations, like design or a multiverse, we shouldn't just shrug and say, well, it's just a coincidence. The fact that we can even conceive of these explanations suggests they're worth considering.
So it's not enough to just dismiss it as chance. We need to explore the alternative.
That's Leslie's argument. But then Cora Jewell comes along with a different perspective. He says maybe the fine-tuning isn't as surprising as it seems.
How so?
Well, he argues that life is probably causally ramified. That means its existence depends on a whole bunch of independent factors, like a huge chain of events that all have to go right.
So it's a long shot, but it's the nature of life itself.
Exactly. If life is inherently complex and depends on lots of things, then it makes sense that it would be sensitive to all these different parameters, the constants, the initial conditions, everything. So maybe the fine-tuning is just a consequence of life being so complex, not something that needs a special explanation.
It's like saying that building a skyscraper requires a ton of things to go right, but that doesn't mean it's a miracle when one gets built.
That's a good analogy. And it highlights this key debate about whether the fine-tuning is truly surprising. Leslie and others, they think it is surprising, especially if we imagine ourselves not existing yet and then discovering this universe. Jewell, on the other hand, he thinks that given our existence and the complexity of life, the fine-tuning might not be so shocking after all.
Though different perspectives on how surprised we should be. Now, some people hope that future physics will solve the fine-tuning problem altogether. Maybe there's a deeper theory that explains why the universe has to be this way.
Right. It's like the theory of evolution, explaining those intricate biological features that seem so finely tuned for survival. Maybe there's a similar principle in physics that makes our life-friendly universe inevitable.
Einstein famously dreamed of a theory of everything, A theory so perfect that it would uniquely determine the laws and constants of nature, leaving no room for chance or fine-tuning.
Einstein's vision was beautiful. He imagined a theory so elegant and self-consistent that there would only be one possible set of laws, one possible universe.
Wow.
If we found that theory, the fine-tuning problem would vanish. It would just be the way things have to be.
That would be amazing. But what about string theory? It's often touted as a potential theory of everything. Does it solve the fine-tuning problem?
Unfortunately, not really. String theory aims to unify all the forces and particles. But as we understand it now, it doesn't lead to a unique prediction for our universe. Instead, it seems to allow for a vast number of possible vacua, each with its own set of laws and constants.
So instead of one universe, string theory gives us a multiverse.
That's what it looks like. It's like string theory opens up this huge landscape of possible universes, each with its own unique properties. So instead of explaining why our universe is the way it is, string theory just adds more possibilities.
Okay, so string theory doesn't give us the answer we hoped for. What about dynamical explanations, like inflationary cosmology?
Inflation is an interesting case. It tries to explain some of the large-scale features of our universe, like its flatness and smoothness. It says that the very early universe went through a period of extremely rapid expansion, which smoothed out any initial wrinkles and drove the density towards the critical value.
So it explains some of the fine-tuning, but not all of it.
Exactly. Inflation might explain the overall shape and some large-scale properties, but it doesn't really explain the specific values of most of the fundamental constants. And it doesn't account for many of the other fine-tuned features we've discussed.
So it's a partial solution, but we still need something more to explain the full range of fine-tuning.
Right. And that brings us back to the big philosophical responses. Design and the multiverse. We've already touched on them, but let's dive deeper into the arguments and objections.
Let's start with design. The idea that the fine-tuning is evidence for a cosmic designer, some intelligent being who intentionally created the universe to be life-friendly. It's a classic argument going back centuries.
It is, and in modern times, it's often framed in probabilistic terms, using something called Bayesian reasoning. The idea is to compare the probability of observing our life-friendly universe under two different hypotheses, one with a designer and one without.
So we're basically asking, how likely is our universe if there is a designer, and how likely is it if there isn't?
Exactly. Proponents of the design argument say that if there's no designer, the probability of getting a universe with all the right conditions for life is incredibly small, given all the fine-tuning we've seen. But if there's a designer who wants to create life, then the probability of a life-friendly universe goes way up, maybe even close to certain.
It makes intuitive sense. If you imagine a powerful being who wants to create life, it seems reasonable that they would create a universe capable of supporting it.
It does. But there are some strong objections to this argument, and one of the biggest is the anthropic objection.
The anthropic objection, that's the idea that we can only observe a universe that allows for our existence, right? So maybe it's not so surprising that we find ourselves in a life-friendly universe.
That's the gist of it. It's like a puddle, thinking that the hole it's in was perfectly designed for it, when in reality it couldn't exist in any other shape.
That's a good analogy. So just because we observe a life-friendly universe doesn't mean it was designed that way.
Right. And Elliot Sober, a philosopher who's a big critic of the design argument, he argues that the relevant probability isn't just a probability of a life-friendly universe in general, but the probability of a life-friendly universe given that we exist to observe it.
Okay, so we have to factor in our own existence. How does that change things?
Sober argues that when you do that, the probability difference between the design hypothesis and the no-designer hypothesis disappears. It's no longer more likely that a designer created the universe, even with a fine-tuning.
So the anthropic principle weakens the design argument.
It does. But the anthropic principle itself has faced criticisms. There's this famous thought experiment called the firing squad.
The firing squad, I've heard of that. What's the idea?
Imagine a prisoner who's about to be executed by a firing squad. They're blindfolded, they hear the shots, but they're still alive. Now, according to Sober's strict anthropic reasoning, the prisoner shouldn't be surprised. After all, they couldn't be contemplating their situation if they were dead.
Okay, but intuitively it seems like the prisoner has good reason to think the firing squad missed on purpose.
Exactly. And philosophers like Dennis Weisberg and Aaron Kotzen have argued that Sober's version of the anthropic principle is too strong. It doesn't properly account for the evidence we have in situations like this. They think we should treat anthropic bias as a form of evidence itself, not just background information.
So the debate about the anthropic principle gets pretty subtle.
It does. And there's another challenge for the design argument, the problem of old evidence. We've known for a long time that our universe supports life. We're here, after all.
So how can we use that as evidence for a designer if we already knew it before we even thought about the designer hypothesis?
That's the problem. It's like trying to prove that the sun exists by pointing to the fact that it's daytime. To get around this, some philosophers, like Robin Collins, have proposed this idea of probabilities.
Probabilities. That sounds interesting. What are those?
It's a way of thinking about probabilities before you have any knowledge of the world. Imagine a hypothetical agent who doesn't know anything about the universe, not even if life exists. Then imagine they discover that the universe is fine-tuned for life.
Okay, so we're trying to get back to a state of ignorance before we knew about life.
Right. And the idea is that this discovery would be genuinely new evidence for them, evidence that could be used to update their beliefs.
And how does that help with the design argument?
Well, from this probability perspective, the existence of life becomes evidence for a designer because it's a surprising discovery. It's like finding a watch in the woods. You wouldn't assume it just appeared by chance. You'd infer a designer.
Okay, so we're shifting the focus to the surprise of discovering a life-friendly universe.
That's the key. But even with this probability approach, there are still challenges. Like, how do you assign a prior probability to the designer hypothesis itself? How likely is it that a designer exists in the first place?
That's a tough one. We don't exactly have a lot of data points on cosmic designers.
We don't. And critics argue that any attempt to assign a prior probability to the designer hypothesis is going to be subjective and ultimately based on faith.
So the design argument, even with these sophisticated philosophical maneuvers, still faces some fundamental challenges.
It does. And on top of that, there are other issues. Like, if there is a designer, what are their motivations? Why create a universe with so much suffering, for example?
That's the classic problem of evil. It's hard to reconcile the idea of a benevolent, all-powerful designer with the amount of pain and suffering in the world.
It is. And even if we could somehow figure out a designer's motivations, there's still the problem of explaining the designer themselves. Where do they come from? What are they made of? Are they also fine-tuned?
It seems like every answer just leads to more questions.
It often does, and that's why some people find the multiverse hypothesis more appealing. It offers a different kind of explanation, one that doesn't rely on a supernatural designer.
Right. The multiverse, the idea that our universe is just one of many, maybe infinitely many universes, each with its own laws and properties.
Exactly, and the appeal of the multiverse is that if there are enough universes with enough variation, then it becomes statistically likely that at least one of them will have the right conditions for life. We just happen to be in that lucky one.
So instead of a designer, it's just a matter of chance, but on a cosmic scale.
Right. With enough universes, even extremely improbable events become likely somewhere. The anthropic principle plays a role here, too. We can only observe universes that allow for observers.
So it's not surprising that we find ourselves in a universe that supports life. It's a selection effect.
Exactly. And just like with the design argument, there are different ways to frame the argument for a multiverse. Some people see it as an inference to the best explanation.
Like the multiverse is the simplest, most elegant way to explain the fine-tuning.
Right. It avoids the need for a designer or any special purpose. Others try to make the argument more rigorous using probability.
So comparing the probability of a life-friendly universe in a single universe scenario versus a multiverse scenario.
Exactly. And if the multiverse is big enough and diverse enough, the probability of at least one life-friendly universe goes way up, maybe even to 100%.
But we run into the old evidence problem again. We already know our universe is life-friendly. How does that affect the probability calculations?
It does. And applying the probability approach to the multiverse is tricky. It's not clear what background knowledge a hypothetical observer should have before they discover a multiverse. Some philosophers worry that we might be double-dipping, using the fine-tuning itself to justify the existence of a multiverse, which would be circular reasoning.
So even the multiverse argument has its philosophical wrinkles.
It does. And it faces other criticisms, too. One of the biggest is the inverse gambler's fallacy.
The inverse gambler's fallacy, what's that?
It's the idea that you can't infer a large number of past events from a single remarkable outcome. Like if you walk into a casino and see someone win a jackpot, You can't conclude that they must have played a million times to get that lucky.
Okay, I see. So how does that apply to the multiverse?
Critics argue that the multiverse argument is making a similar mistake. They say that just because our universe is life-friendly, we can't conclude that there must be tons of other universes where it's not.
But proponents of the multiverse push back on that. They say we're not just randomly observing a universe. We're observers who can only exist in certain types of universes.
Right. Peter McGrath uses this casino analogy. Imagine you're only allowed into the casino if someone wins a jackpot. Then seeing a jackpot wouldn't be surprising. It would be the condition for you being there.
So our existence as observers changes the probabilities.
Exactly. But critics like Timothy White argue that this analogy doesn't quite fit. We weren't waiting outside a multiverse for a life-friendly universe to appear. It's a complex debate, and there's no easy answer.
So the inverse gambler's fallacy argument is still a point of contention. Another challenge for the multiverse is finding evidence for it. If there are all these other universes, can we ever see them?
That's the million-dollar question, literally. By definition, other universes in a multiverse are usually thought to be causally disconnected from our own. That means we can't directly interact with them or observe them.
So how could we ever know if they're really there?
It's tough. Some physicists hope to find indirect evidence, like subtle patterns in the cosmic microwave background radiation or anomalies in the distribution of galaxies. But these are long shots.
It seems like the multiverse might be inherently untestable.
It might be. Some proponents of the multiverse argue that even if we can't directly observe other universes, the fact that